Hello everyone, and today we're going to be talking about the Kalman filter. We finally got here. Now while this video is going to do a derivation of the Kalman filter, we're going to be focusing a little bit less on the derivation and more on the intuition behind the final equations. What we want to do is connect what we know about robotics that we learned in week 3 from particle filters and connect that to the math that I'm showing here in the Kalman filter equations. So before we get into that, I want to talk a little bit about vocabulary. So we have this a priori estimate, and what that means is what is my estimate of my vector x when I have every sensor reading up until the most recent one. Right now we are at some time k. So since I have all of my sensor readings of 1 to k minus 1, this is my a priori estimate. I'm going to use this minus sign here to denote that. So my posteriori estimate is the exact same thing as my a priori estimate, but now I have that final sensor reading. And I denote that with a plus. And then there are other types of estimates that you can use Kalman filters for. Let's say that we're running this offline, which means we don't have to get an estimate as we drive around, and I have sensor readings into the future. I can incorporate that also into my Kalman filter like this and get a smoothed output of what I saw. This essentially allows you to post-process the position of your robot or the state that you're predicting with your filter. So we have the same thing for covariance. So I have my covariance after I included my last sensor reading, which is why I have x hat of t plus. And then I have my a priori covariance, which is before I've included that. So I'm only using the sensor readings to t minus 1. So all I have is y1 to y of t minus 1. Here I have y1 to yt. And this is going to give us explicit equations for our covariance. So if you remember in the third video, we derived these equations for updating the mean and covariance given some dynamics. So we have our dynamics here, and this is our update equation for the covariance. And remember, this q comes from the fact that there's actually a plus omega t here. What we're looking right now is at the mean update equation. So in expectation, this wt goes to 0, because if you remember, wt is a random variable that is normally distributed between 0 and q. So this q here corresponds to our process noise, or how much noise we have when we move around. So as we move, we increase our covariance, and that is related to q. So now let's look at a bunch of equations. So what we have here are the equations that we derived for the least squares estimator, as well as the final Kalman filter equations. I'm going to point out something that's really cool. So these three equations here are actually just these three equations here. This equation, and this equation are all exactly the same. The difference you have is that what are my inputs? So in this, I'm using my prior covariance and my prior estimate of the state. But now I expect that my state has moved. So I must use the motion update equations that we just talked about to move my state, and then I'm going to get my a priori estimate. And if I use my a priori estimate in a recursive least squares estimator, I get out the form of a Kalman filter. So that's all we're doing here. We've derived all of the math already. All we're doing here is using our expected motion of our distribution to aid in our filtering. So what we're going to do is we're going to break down these equations in a couple steps and look at kind of the intuition of what's happening behind all of them. So as we talked about before, this is our time update equation, or our motion model. So we have, this is our update for the covariance, and this is our update for the mean of the state. And these just follow our motion equations exactly. So this is just the expected value. So we get wt goes to 0. And then this equation we derived earlier, and this corresponds to our process noise. So how much extra noise we want to add into how we think our state could be moving. So having a Q matrix that is non-zero can help even if you're tracking a stationary point like we're going to be doing in this week. And this prevents the covariance from converging to 0. Because if Q is equal to the 0 matrix, this essentially drops out, and we are left with this equation here. So this equation will increase over time, but it could increase at a very slow rate, and depending on how our sensor model is tuned, we could drive our covariance to 0. Having a non-zero Q explicitly prevents that. And this is what you want, because covariance collapse is a very real issue with Kalman filters. So next we have our gain matrix, K. And K has a really important part of the equation, which is here. And this is often called the innovation matrix. And it has an important property. And it's inversely weighs sensor measurement errors. So if we have a sensor that is too noisy, the corresponding entry in R will be high. And by taking the inverse, which is what we're doing here, measurement from the sensor will be weighted less. So essentially what this is saying is, how much should I care about my sensor reading? If I'm very confident in my sensor reading, what we're going to see a little bit later is that we're going to more weight the sensor reading. So moving on to the sensor update. And remember, this is based on the estimation of how our filter has moved. So this K-matrix says how much do I want to trust my sensor reading? And remember, this has the equation R in it, which comes from our noise on our measurement model. So this essentially, you can think of it like a weighting of how much do I want to change my state based on my sensor reading. That's what K is doing here. And the final equation is how we update our covariance based on our sensor reading. And what you can see here is this has the same idea of K, so how much do we trust our sensor readings, times R, which is our confidence in our sensor readings, and a value that corresponds to something very similar times our propagated covariance, P minus of K. So essentially it's saying, how much do I want to trust my prior covariance, and then I'm going to modify it based on my sensor reading. So if we put all these equations together, we get out the final common filter equations shown below. And what you're going to have are two main steps. So we break the equations here. So in this first step, what we're going to do is we're going to do our motion update. And then in the second step, we're going to do our sensor update. And this corresponds to something that looks like this. So if we start off, we have some position, x0, and then we have some covariance around it. So we would have x0 plus, and then p0 plus. And then what we're going to do is we're going to move. We're going to apply some actuation. But by doing so, we increase our covariance. We move our mean. And this gives us x1 minus and p1 minus. And this is our motion update. Then what we're going to do is we're going to shrink our covariance based on some sensor reading. So let's say I got some sensor detection here, and based on that I'm able to predict some new mean and some new covariance. And this would be x1 plus and p1 plus. So now that we've incorporated our measurements, we get to the pluses. You're going to keep repeating these steps over and over again. So next we'll have some x2 plus and p2 plus after we've both moved to get the x2 minus and p2 minus. And then we shrink our covariance again. So this is all the common filter is doing. It's recursively applying these equations to propagate our distribution and then refine our distribution based on some sensor reading. So if we go back to our example of our robot, we're trying to track our mineral deposit. So let's say the ground truth of our mineral deposit is here, and then we have our robot that starts here. As we drive around, we get more and more detections, and those detections will show up like this. So those actual detections will be giving us x, y positions directly. So when we go to compute our H matrix, what we're going to get is a matrix of 1s. Because our sensor reading is the exact value we're trying to predict. We're trying to predict the xy value of the mineral deposit, and we're given sensor readings on the xy value of the mineral deposit. But you need to find the center. And since there's a decent amount of noise, it'll be difficult to find the center without a Kalman filter. Finally, even though there is no motion of our state, we're always assuming that the point is fixed. We're going to have a Q, which is going to be a very small value like this. And the reason we do this is just to prevent our covariance from decreasing to 0. In summary, what we've done in the last 4 lectures is we've started out with some idea if we have a sensor reading and we have some motion model. We derive the least squares solution to filtering. So this allows us to have a mathematically sound way of predicting a state vector given some noisy sensor readings. Then we took that, which was required to be applied in a batch setting, and extended to the recursive format here, which is using recursive least squares estimator. And then what we finally did is we went, oh, well, this relies on a static state vector. Can we incorporate some idea of the motion of the state vector? Can it move forward in some meaningful way? And then we extended that to encompass moving filters, and that problem gives us a Kalman filter. So the actual derivation that we did here and here did most of the mathematical lifting, and all we had to do was combine these equations together to give us the Kalman filter. This is a really common thing in robotics. You're going to have a lot of different things that look very mathy at first, but if you take it step by step, you'll see that it's pretty easy to build up these different algorithms. That's all for this week.